So first thing I want to do today is I want to keep talking about the fundamental theorem of calculus. So what was the fundamental theorem of calculus that we saw so far? It was this thing, which says that if you take the integral from a to x of f prime, then what you wind up with essentially is your function back. You get f of x minus f of a, and of course f of a is just kind of like your constant. So if you like, you can think of it as the plus c. So using the plus c form, it'd be like a plus c. But using the fundamental theorem of calculus form, it looks like this. And of course, we saw how to use either form to solve a problem. But the long story short is what this says is, if you have a function, then you take the derivative, which gives you f prime. Then you take the integral again, you get the function back. So this is the sense in which taking an integral and taking a derivative are opposite things. And sometimes we just call the integral the antiderivative because we want to emphasize that fact. Okay. Right. The notation is tricky. We went through why, but that's the basic idea. Now, having said it this way, this implies that something else might be true as well. If I have a function, I take the derivative, I take the integral, I get the function back. Well, then what else might also be true? If I have a function, dot, 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 and then I get the function back. That's what this one is.
They're not inverse, so they're...
Take the integral and then take the derivative?
Exactly. If I have a function, and then I take the integral, and then I take the derivative, should I get the function back? Yeah. That sounds right. So let's see if it's actually true.
It's not totally true, because the c disappears. If we take the derivative,
First we're taking the integral, and then we're taking the derivative.
Okay.
So does the c disappear? That's a good question. Okay. It turns out that this is actually precisely correct, and it's easy to show. Wait for you guys. Okay. Okay. So we're going to start with a function. And again, we're not going to start with f prime because we don't want to talk about taking a derivative yet. So we're just going to start with a function, call it little f. Okay. So we take the integral of that. So in other words, what we're doing is taking the antiderivative. Okay. So the integral, so here's what so let's take so remember I said when we have a little f and a big F, we're going to assume that big F prime is little f. That's the relationship that we assume. Okay, so if you take the integral from a to x of little f, what do you get? You get, by the fundamental theorem of calculus that we already know, you get big F of x minus big F of a, where derivative of big F is little f. Okay. Well, now we just took the integral. Now let's take the derivative of that. So when you take the derivative, what happens?
you get the same thing.
The same.
Right. Well, we got to think about two things. Big F of a. What is that?
Constant.
It's a constant. So when you take the derivative, goes away. And and big F of x. What's the derivative of that?
Little f.
It's just little f. Proved. Done.
But
It was easy to prove because we already had this beautiful thing, Fundamental Theorem of Calculus Part 1, to help us, which makes things very, very easy. So now we know that when we take the integral, then take the derivative, you just get the original function back. So there you go. So the Fundamental Theorem of Calculus has two parts, Part 1 and Part 2. There they are. And again, we've talked about why the notation is a little tricky, but the idea behind it is very easy to say.
so what's the point?
So the point is, this actually helps us do problems really easily. You wouldn't be able to take an integral. So, okay. The way that I showed an integral to you, I said, hey, look, an integral is really the opposite of doing a derivative. Or I said, what if we knew derivatives? How could we recover the original function? And we did some things and we said, oh, we're going to call that an integral. Now it turns out that that is actually not the way that integration was originally developed. Originally, derivatives were talked about in one way, and integrals were talked about in a completely different way. And that was done for something on the order of like 100 or 200 years. And so perhaps you've heard that Newton and Leibniz in the 1640s were credited with discovering calculus. So the reason they were credited with discovering calculus is because they took the derivative and the integral and they said, hey everyone, they're actually related. So the discovery of calculus is actually the discovery of the thing that I just showed you. At least that's how it's interpreted in the history of math. So the fact that I just showed it to you this way, I've cleaned up a lot of the details.
So wait, are you telling me that Newton and they didn't come up with the derivative or the integral, they just came up with the relationship?
Exactly. So little techniques. So some techniques of how to do a derivative in some instances, that was already known. Some techniques of how to do an integral in certain instances, that was already known. But they made this broad and general. They said we always know what the integral is if it's the derivative of another function. Automatically you can do the integral, it's done. As opposed to all these, so for example, I showed you this Euler approximation technique. So there were all different kinds of approximation techniques. Because that was the only way that they knew how to do integrals. Because they didn't know this. And that's what was going on for something like 100 or 200 years. This cleans up all that mess of not actually knowing how to do an integral. Okay.
In the notation, just to clear something, when you introduced the FTC the first time,
Yeah.
the fundamental, the notation for f of x minus f of a, it was f. Wasn't it f prime of x minus f of a, not f? So it's always f. Oh,
Yeah.
because our original function in that case was the antiderivative. That's why it was just f and f.
Well, the way that I originally presented it to you was by saying, let's start with little f prime. So when you take the integral, you get little f. But that was the case where we first took the derivative and then we're taking the integral. So here, I don't want to have primes in my original statement because I don't want to talk about taking derivative yet. Here, I just want to start with a function, then take the integral, then take the derivative. So I'm starting with little f, doing the integral gives me big F, and then I take the derivative, and that gives me big F prime, which is little f. It can be confusing. The main thing to keep in mind, in fact, as we were talking about with the homework, the main thing to keep in mind is what's the relationship between the functions? Am I taking derivatives or am I taking antiderivatives?
If I were to write the previous function, the first time you did it originally would be f prime of x minus f prime of a equal the integration of f prime of t.
We have to be clear about big F and little f, but if you like, just jot notes to yourself on the side, like here's my original function, here's its derivative, or here's its antiderivative, da da da. You know, just keep track of. I like to think of it as like a ladder. You know, we're going up the ladder or down the ladder. Are we taking derivatives or antiderivatives? So keep in mind which is your original function, and then if you're doing antiderivatives or derivatives. But that's the confusing thing. So that's the most important thing to keep in mind to orient yourself as far as what's going in the problem. Exactly. Okay, so now that we have this fundamental theorem of calculus part 2, we can do problems like this. Okay, so what do we do here? Well, there's two ways to do this problem. One is the old way. The old way is, well, let's take the integral. So if you take the integral, what do you get? Well, the integral of t squared is t cubed over 3. So you're going to have t cubed over 3 evaluated from 1 to x. And then, of course, when it's all done, we're going to take derivative of that. So then that equals, here. Actually, let me do this like this. So then that equals x cubed over 3 minus 1 cubed over 3, which is just 1/3. But again, more room. Okay. But now that I've got this, I want to take the derivative of it. So when you take the derivative of that, what happens? Well, derivative of x cubed over 3. 3 comes down, it cancels. You just got x squared, and then the derivative of the other piece, it's a constant, so it's just 0. So you just get x squared. The 3 cancels with the 3. All right. So that's the old way that we already could have done it. But now, what's the new way? The new way is, well, I've got a function. I'm taking the integral. Now, again, it's important to understand that the integral itself is a function because it's the integral from 1 to x. So it's going to give you a function, and we talked about making that distinction. So when you take the integral, it's going to give you a function of x, but then we're going to take the derivative. So have a function, take the integral, take the derivative, what do you get back? The original function. So you just get x squared. So fundamental theorem of calculus 2, you just do this in one step. That's, yeah.
I'll do it again. Now you tell.
I mean, there's nothing to do. It's just understanding the fundamental theorem of calculus number 2.
If you don't understand it, use that one.
The problem is that you can't necessarily. So now I always start off with an example that you can do either the old way or the new way. Now, okay. Oh. Why is that there? Oh, okay. Okay. All right. So I want to make 2 more examples. So first of all, I want to point out that we talked about in terms of notation, which one is the variable in the function, and then which variable is going to kind of disappear. So keep in mind, in the first example we did, t was kind of like the dummy variable, which when you integrate, you're just going to plug in x. So as far as which is the variable that's going to appear in the function, it's actually x. So when you do your integral, you're going to plug in x, then you take the derivative with respect to x. So now I've written out this new problem. Here you're starting with x, but when you integrate, what's the variable that you're going to have? T. You're going to have t. Then you take the derivative with respect to t. So what's the answer to this problem going to be? The answer is just going to be t squared. Okay. So now I want to do another example. Let's say, sure.
What do you need a dt or dx in M?
You don't need it. That's the question I'm asking.
You need it and you're asking us.
This is the question I'm asking is how do you find d dx of the integral of blah blah blah? That's what I'm asking.
Dx.
Sorry?
I'm thinking like the 2 variables dx and dt at the end. Yeah, you really need them or you don't?
Oh, you mean at the end of the integral? Yes. Let me come back to that. I want to ask this one question first. Yeah, Paul.
What if you change the limits of integration? You don't integrate it up until x. What if you change it to like x cubed, x additional? Like
You're ahead of me by about 1 minute. So we'll get there in 1 minute. Okay. So what about this? So what about, let's see, I don't know, cosine of e to the t, I don't know, times t squared over t.
Look at the example. It just says t, right? It's integrated.
There you go. Okay. So what if I tell you to do this? Do you want to go ahead and first calculate the integral, then calculate the derivative? No, that integral is disaster. I'm not even sure if it can be done. Maybe it can, maybe it can't, I don't know. Oh, wait a second. There, now you can't factor it. Okay. So the point of the fundamental theorem of calculus is that it doesn't matter whether or not you can actually first do the integral. Because you know that the point of this problem is to do the integral, then do the derivative. And when you do that, what does it give you? It just gives you the original function. But what's your variable going to be? Yeah. So the answer to this is cosine of e to the r squared over 1 plus r.
So what's the point? It's the same exact thing. I mean, just
Right.
The concept to understand that,
Yeah.
that they're
But if I hadn't told you how to do this problem, would there be any way to do this problem? No. Without the fundamental theorem of calculus number 2, this is an impossible problem. With the fundamental theorem of calculus number 2, it's so trivial it makes you ask questions like, what's the point? And that's the powerfulness. That's how powerful that theorem is. It turns something that's completely undoable into something that's completely trivial. So that's the point.
they're like basically the opposite operations. That's the fundamental that it
Exactly.
proves that they're opposite operations.
Yes. Exactly.
That's the point. Again, you can put dt at the end when you use dt.
Let me come back to that. Okay, so now I want to get to Paul's question. Paul's question was, what if the limit of integration isn't just, in the last problem it was r, before that it was t, before that it was x? What if it's something funky? Like this. Okay, so you said what if it was x squared? I'm going to put sine x. Either way. Okay, so how do you do this? Okay.
Just make sin x a different variable and do the problem like regular and then plug in for sin x.
Why just not plug in for sin?
So, right. So what do you guys think the answer is to this problem? Okay. So it looks like the answer is going to be sine x to the third over 0. You just say I'm integrating from 0 to sine x, so that's what I'm going to plug into the original function. Instead of x, I'm plugging in sine x. Okay. You're half right. And what? Exactly. And let's look at why that happens. Okay. So what happens? So first of all, let's say that the function is t cubed. Okay. So we know that f is some function such that, or big F is some function such that big F prime is little f. So in other words, the usual thing that we say. Okay, so when we first do the integral, what happens? So it's going to be big F, big F of t, evaluated from 0 to sine x. And then when we're done with all that, we're going to take the derivative. Okay. So what does that give you? That gives you big F of sine x minus big F of 0. And I always forget to write derivative in front. Sorry. Let me make this nicer. Okay. Okay. So first, the easy part. When we take the derivative of f of 0, what happens? It's the constant. Derivative is 0. It goes away. Now, what happens when we take the derivative of big F of sine x? It's the chain rule. Exactly. So the chain rule is going to look like this. It's going to be big F prime evaluated sine x, but then what? Times the derivative of sine x, which is cos x. So when you finish working it out, but what is big F prime? Big F prime is just little f, which was our original function. So that's just sine x cubed times cos x. So this is the hard case where you can't just stick it into the original function. Does that make sense? So the reason you can't just stick it into the function is that when you actually go through the steps, what you see is there's a chain rule in there. Now, of course, if the boundary of integration was just x, when you do the chain rule, the derivative is 1. It doesn't change anything. So you don't need to worry about it, like always. But if the boundary of integration is not just x, but it's some function of x, when you step through it, you see, I actually have a chain rule. I have to take the derivative of whatever that thing is. Sorry? Yes. So little f is t cubed. So when I get to the end of the problem, I know that big F prime is just the same as little f. So it's just sine x cubed, because that's my original function. But by going through all this, we see that not only do we just have the original function and plug it in, because of the chain rule, you also need to take the derivative of sine x. So another point is that by understanding the mechanisms of the fundamental theorem of calculus number 2, you can see why there needs to be a chain rule there. So understanding doesn't hurt either.
So cosine x is not x to the third, it's just cosine x.
It's the chain rule where after taking the derivative of the outside function, you then multiply by the derivative of the inside function. The inside function is sine x, and the derivative of that is cosine x. It's the chain rule. Oh, right. So, yeah. Okay. So this is the final and big version of the of the fundamental theorem of calculus number 2. So finally we have d dx of the integral from a to u of x, where u is just some function instead of just x, of f of t dt equals f of u times du dx. Yeah. So in general, the original form of the fundamental theorem of calculus number 2 is good enough, because you're usually only integrating from 1 to x. But sometimes you have this more difficult version. Just remember, it's the chain rule, and the derivative pops out.